This project is about how to save energy in large-scale data centers. My name is Jessica, and I've worked on this project with Yanis, Sangte, and Professor Chang. As you know, all the jobs that arrive to a data center are not time elastic, which means that some jobs, like data synchronization and backup jobs, can be postponed until a later time. And this gives us an opportunity to optimally balance energy and delay. What this is an experimental implementation of the theory on optimal sleeping that we heard earlier. The way it works is that job generation keeps on producing jobs and placing them into a queue that we can see here. In the meanwhile, a controller continuously checks the status of the queue to check whether the number of jobs in the queue has reached certain thresholds at which we turn on or off these servers. And these thresholds are decided by the value iteration algorithm that's used to find the optimal sleeping policy that our theory dictates. The controller basically decides when the number of jobs in the queue have reached a sufficient threshold at which it turns on one or more servers. And if ever the jobs in the queue fall below a certain threshold, the controller starts to turn off the servers. All the servers are connected to a power meter, and the power meter continuously logs every second the total power consumption of all the, in our experiment's case, 3 servers. So now we can go ahead and look at the actual experimental implementation. Okay, so now that we're here at the experimental setup, let's look at a few key terms and how they correspond to our actual hardware over here. So this computer that we have here is the controller that I explained about earlier. The controller controls these 3 other servers and turns them on or off as per the thresholds generated by the value iteration algorithm. And it's also responsible for assigning them jobs as in when they get free. Jobs are generated as per a Poisson arrival process, and in the context of this experiment, a job is video encoding and also playing a video on the screen so that you can tell when a job is running. So these 3 are our servers, and over here we have our power meter. The power meter logs every second how much power is being consumed by all 3 of these servers together. Right now it's really low because all 3 of these servers are asleep. Now moving on, when I actually start to run the experiment, you'll see a couple of plots dynamically changing. But before I run the experiment, let me just talk about these first 2 plots that we see here on the screen. The first plot over here shows us some turn on and turn off thresholds. These are thresholds that were generated by theory, the value iteration algorithm, as I mentioned earlier. And they basically tell the controller when to turn on and turn off servers depending on the number of jobs that are waiting in the queue to be executed. So if we look at this turn on policy, we can see that when we actually hit 2 jobs in the queue, we'll be turning on our first server. And furthermore, when we hit 5 jobs in the queue, we'll be turning on our second server. And a similar reasoning can be applied to the turn off policy as well. When we fall below a certain number of jobs in the queue, we'll actually start to turn off some servers. The second plot that we see over here is actually a very important one. It's our energy delay trade-off curve. As we can see, it's a Pareto optimal trade-off curve. Each point on this graph has been generated through an experimental run with this experimental setup. And each point represents a different tolerance for delay versus energy saving. So for example, if we're interested in really conserving a lot of energy, but we're not that concerned about time delay incurred by jobs waiting in the queue, we operate at this part of the graph where the time delay per job is higher and the energy consumption is actually lower. Whereas if we're really concerned with getting all our jobs done on time and not making them wait in queue for too long, we operate in this part of the curve where the energy consumption is high but the time delay incurred by each job is lower. Finally, before we actually start running our experiment, let's just quickly take a look at these 2 plots and talk about what we expect to see from them. This first plot here shows us the number of jobs that are actually in the queue, so this is the status of the queue. And you'll see when the experiment starts running how the status of the queue directly corresponds to the servers turning on and off as per this on and off thresholds plot over here. And the second plot that we see over here is our power consumption over time. Basically, each second our power meter tells us how much power is being consumed by these three servers put together, and we keep plotting this in real time. As you can see now, the line is really flat because all three of the servers are asleep and are not really running jobs yet. So now we can move on to running the actual experiment. Before I start that, as you all probably know, when we move from theory to actually running something like this in experimental form, there are a lot of problems and challenges that we face along the way. Some of which are, one point is that in theory it's really easy for us to say that turning on or turning off takes a certain amount of time, and we can assume that after giving a sleep command and after a certain amount of time elapses that a server will be asleep. But we see in the experimental setup that this is actually not true. It doesn't actually take the same amount of time for a server to go to sleep and turn on every time. Another challenge that we faced are the problem of critical sections, like the status of the queue needs to be accessed by all three of the servers at the same time, but it also shouldn't be changed at the same time by more than one of them. So taking care of that, taking care of simultaneous generation of jobs and allocation of jobs to servers, things like this were challenges in the setup of this experiment. But now we can see I'm actually going to run this experiment. And we can see, so initially the status of the queue is 0, there's no jobs, all of the servers are sleeping, and we can actually see that they're all sleeping while the experiment starts to get initialized. Slowly we can see it looks like there's one job in the queue. So our jobs are being generated as Poisson arrivals, and now it looks like we've hit the first threshold, and soon after that we hit the second threshold. So we have two servers on. Both of them are running jobs, as you can see from these clips of video. And as well, on the power consumption curve, we can see that our power consumption just spiked because we turned on two servers and also we're running jobs on both of them. Now you can see this third spike. That's because I can see here that the third server has also been turned on because we hit our third threshold. And the third server is also running jobs. And so that's because the status of the queue dictates that all three of the servers should be on and all three of them should be running jobs. So if we keep watching this experiment over a certain period of time, we'll notice that the status of the queue will increase to the point where all three of the servers are on running jobs. Of course, if the jobs are being executed in a timely manner, the status of the queue may go down, and when we fall below certain thresholds, we'll actually begin to see some of our servers turning off, and then we'll watch the power consumption also go down based on us turning off those servers. Okay, so now we can see from the status of the queue that the number of jobs in the queue has actually fallen below two thresholds, in fact, that it turned off both these servers, but then it came above one of our turn on thresholds again. So as you can see, we just turned on this other server, but the number of jobs in the queue is still not enough to warrant that server being on, so that server is asleep. And this is how we actually are conserving power, because when that server is asleep, it's consuming almost no power at all. And we can see this from the power consumption plot. We were operating at a very high power consumption level because all three of the servers were on and running jobs. But then two of the servers were turned off to sleep. That's why we went down there. Soon afterwards, one of our servers was turned on again. So now we're operating at like a middle level where two of the servers are on and running jobs, but the third one's asleep. And this corresponds to the status of the queue. And the turning on and turning off is as per our on and off thresholds from this plot. So something that you might be wondering is, why don't we just always turn on servers when we have jobs in the queue and then just turn them off when we don't have enough jobs in the queue? Why have an optimal threshold policy at all? This is because of the switching cost. And this basically means that to turn on or turn off a server, it takes a little bit of energy and it also takes time. So the reason we implement this theory to this experiment instead of following a naive solution is because we need to take into account the fact that it takes time for us to switch off computers, and it takes time for us to turn them on again. And also, there's a little bit of peak in energy consumption when we're actually doing things like this. So we need to consider factors like this when we're implementing this policy. We're also really excited about extending this work in the future. Some future things that we're thinking of implementing are the same experiment except for heterogeneous cores. Right now we're assuming homogeneous cores. Another thing that we're interested in doing is comparing this algorithm to a greedy algorithm, which, as I mentioned before, would just turn on servers when they need to be turned on and turn them all off when there are no jobs left in the queue, and compare our readings from this sort of experiment, which uses theory to predict thresholds rather than a greedy algorithm like that.
Yeah, thanks for Google and Princeton Grand Challenge to support this research. Thank you very much.